An invisible light permanently bathes the entire cosmos. This is the cosmic X-ray background, a faint fog of high-energy radiation that holds secrets to the most violent events in the universe. By the end of this journey, you will see the empty night sky not as a void, but as a glowing archive of cosmic history. What creates this pervasive light, and why does most of it come from sources we cannot directly see? This mystery connects hidden supermassive black holes to the possible decay of dark matter itself. What do you think is the most surprising thing left to discover in our universe? The year was 1962, and the goal was simple. A team of scientists led by Riccardo Giacconi aimed a rocket-borne Geiger counter at the moon, hoping to detect X-rays bouncing off its dusty surface. They expected to measure a faint echo from our celestial neighbor, a straightforward experiment. What they found instead rewrote our cosmic map. Their instruments registered a faint, uniform glow coming from every direction, a pervasive sea of X-rays that had no single obvious source. It was as if you walked into a room you believed was completely dark, only to find it softly, mysteriously, already illuminated. This was the accidental birth of a new field of study and the first great mystery, the cosmic X-ray background. The discovery was profoundly unsettling. The prevailing view of the universe at the time was relatively serene, especially in the high-energy X-ray portion of the spectrum. Astronomers knew of a few violent stars, but nothing that could account for this all-sky fog. It hinted at a hidden, tumultuous side to the cosmos, a universe teeming with invisible violence. This uniform glow was the first major clue that our quiet universe was an illusion, and it sent scientists on a decades-long quest to answer one fundamental question. What was lighting up the entire sky? For decades, that faint, all-sky glow was a cosmic riddle without a solution. The central question became a matter of accounting, a celestial ledger. What percentage of this X-ray glow could we actually explain? The first step was to find out if this fog was truly uniform or if it was made of countless individual points of light, like a distant city seen through thick mist. Resolving this background became the primary goal for a generation of X-ray astronomers. This required a telescope with vision sharp enough to pick out the faintest specks in this cosmic haze. That tool was the Chandra X-ray Observatory. Launched into orbit in 1999, Chandra was a masterpiece of engineering, capable of seeing X-ray details 50 times finer than any previous telescope. Its mission was to stare at a single, seemingly empty patch of sky for weeks, gathering every precious photon. The results were breathtaking. Where once there was only a smooth, mysterious fog, Chandra revealed a sky glittering with millions of distinct sources. The vast majority of these points of light were active galactic nuclei, the intensely bright cores of distant galaxies powered by supermassive black holes actively feeding on matter. This was a monumental discovery. It showed that the cosmic X-ray background was not a true, fundamental glow, but the combined light of countless cosmic powerhouses, each one a vortex of incredible violence. Yet, the mystery was not completely solved. Even with Chandra's incredible vision, a portion of the background remained stubbornly unresolved. It was as if you counted every star you could see on a clear night, but a soft, pervasive twilight still lingered in the darkness. This unresolved fraction is the new, deeper mystery. What creates this leftover glow? Are they just fainter, more distant versions of the same active black holes, objects so far away that even Chandra cannot pick them out individually? Or does this faint residue represent something entirely different, something more ancient and pervasive? One compelling idea is that we are seeing the collective heat. This could be the glow of incredibly hot gas trapped in the very first clusters of galaxies that ever formed, a fossil imprint from the universe's youth. The unresolved light is a frontier, a ghost in the machine that whispers of discoveries still to come. this faint leftover glow is only part of the story. The real breakthrough came when scientists realized what the majority of those millions of points of light actually were. The cosmic X-ray background is in large part the collective roar of supermassive black holes. Not the quiet, dormant giants like the one at the center of our own galaxy, but their hyperactive cousins known as active galactic nuclei. Imagine a single black hole weighing millions of times the mass of our Sun, with a whirlpool of superheated gas and dust spiraling into it at nearly the speed of light. The friction and magnetic forces in this maelstrom heat the material to unimaginable temperatures, causing it to glow with a ferocious intensity that can outshine an entire galaxy. Now picture millions upon millions of these brilliant beacons scattered across the cosmos, each one a tiny, distant point of X-ray light. Our telescopes see them not as individual storms, but as the combined whisper of their distant violence, a statistical fog that tells a story of a far more active universe in the past. This leads to one of the most puzzling observations in modern astronomy, a phenomenon called cosmic downsizing. It sounds counterintuitive. We might assume that the most massive, luminous black holes took time to build, that they would be more common in the recent universe. But the data from the X-ray background tells the opposite story. The most brilliantly feeding, the most gluttonous supermassive black holes were actually more common when the universe was young. Billions of years ago, the cosmos was a stage for a frenzied black hole growth spurt, a period of incredible violence and activity. Then, over cosmic time, this frenzy quieted down. The most luminous AGN became rarer, and the average black hole meal became much more modest. So the mystery is not just what they are, but what happened. What cosmic trigger flipped the switch on that era of rampant black hole feasting? And why did the universe seemingly settle down? This question ties the faint X-ray glow in our sky directly to the life and death cycles of the most powerful engines in existence, suggesting that the empty space above us is really a graveyard of ancient giants. So the universe's biggest eaters are often hidden from view. This brings us to a deeper layer of the mystery, a population of cosmic monsters shrouded in thick veils of gas and dust. Imagine a lighthouse wrapped in a dense cosmic fog. You might not see its brilliant beam of visible light at all, but a more powerful, penetrating signal could still get through. This is precisely the case with a huge number of the active supermassive black holes that make up the X-ray background. They are known as obscured active galactic nuclei. Their central engines are hidden behind swirling, opaque clouds so thick that ordinary optical or ultraviolet telescopes simply cannot see the brilliant core. This obscuration is a natural part of the feast. When a black hole pulls in vast amounts of material, not all of it falls directly in. Much of it forms a torus, a gigantic donut-shaped structure of gas and dust that encircles the central monster. From most angles, this torus completely blocks our view. But X-rays are different. They are so immensely energetic that they can punch straight through that obscuring fog, allowing our specialized telescopes to see the hidden heart of the storm. This is why the cosmic X-ray background is such a vital record. It captures the true, hidden population of these violent objects. The big question is, just how many of these hidden giants are out there? Current estimates are staggering, suggesting that for every brilliant, unobscured active galactic nucleus we see, there could be several more that are hidden. This completely changes our census of black hole activity across cosmic time. Are these obscured black holes just a random orientation effect where we happen to be looking at the donut edge on, or are they a distinct and critical phase in a galaxy's life? Some theories propose that the obscuration happens during the black hole's most violent growth spurt, when it is feeding so voraciously that it surrounds itself with the very material it is consuming. In this view, the thick shroud is the signature of a black hole's messy teenage years, a period of rapid growth that eventually clears out as the black hole blasts away its surrounding gas. Unraveling this is key to understanding galaxy evolution itself, because the energy from these hidden monsters can regulate star formation and shape the destiny of their entire host galaxy. The faint X-ray fog we see is therefore a collective signal from both the visible beacons and these hidden giants, a chorus of voices from the universe's most dramatic and secretive transformations. But the story of this cosmic glow is not only about hidden black holes. Our attention must also shift from these brilliant points of light to the vast, diffuse structures that stretch across the cosmos. Think of the largest cities on Earth not as collections of individual buildings, but as sprawling metropolitan areas seen from high above, each one glowing with the combined light of millions of street lamps. In the universe, the largest cities are galaxy clusters, immense gatherings of hundreds or even thousands of galaxies bound together by gravity. And these cosmic metropolises are filled with an invisible, searingly hot atmosphere. The space between the galaxies is not empty. It is flooded with a thin, incredibly hot gas known as the intracluster medium. This gas is so hot, heated to tens of millions of degrees, that it does not shine in visible light. Instead, it glows fiercely in X-rays. The collective emission from all these vast, hot atmospheres in clusters across the universe adds its own distinct whisper to the cosmic X-ray background. This presents a profound mystery of its own. How did this gas get so unimaginably hot? The answer is a violent history. As galaxies and the dark matter that holds them together collapsed under gravity to form these massive clusters, the gas trapped within was squeezed and shocked, heating it to these tremendous temperatures. The distribution of this hot gas is not random. It settles into the deep gravitational wells sculpted by the invisible scaffolding of dark matter. By mapping the X-ray glow from this intracluster gas, astronomers are essentially tracing the shape of the dark matter skeleton that defines the entire cluster. The unresolved portion of the X-ray background could very well contain the faint, combined light from the very first clusters that ever formed, a fossil imprint from the epoch when the universe was building its largest structures. So when we look at that faint, all-sky glow, we are not just seeing the ghosts of hidden black holes. We are also witnessing the residual heat from the universe's greatest cities, a permanent record of the violent construction projects that assembled the cosmos on its grandest scale. Yet even these vast, glowing cities of galaxies are not the end of the story. There is another, more elusive structure that permeates the cosmic landscape, a ghostly web of matter that has proven almost impossible to see. This is the warm-hot intergalactic medium, or WIM. Picture the universe not as a collection of isolated islands, but as a single, interconnected network. The galaxies and clusters are the dense, bright nodes, but they are all connected by faint, wispy filaments of incredibly hot gas. This gas is so diffuse, so spread out, that a single cubic meter of it might contain only a few atoms. You could fly a spaceship through it and never know it was there. Yet, across billions of light years, this vast web is predicted to contain a staggering amount of the universe's normal matter, the same kind of matter that makes up stars, planets, and us. For decades, this matter has been missing. Our inventories of normal matter, the protons and neutrons known as baryons, have never added up. A huge portion was simply unaccounted for. The WIM is the prime suspect for where this missing matter has been hiding. The gas is heated to temperatures of hundreds of thousands, even millions of degrees, which means it should glow faintly in X-rays. Its collective, diffuse emission could be woven directly into the fabric of the unresolved cosmic X-ray background. The challenge is monumental. How do you detect something that is everywhere and yet, from our perspective, almost nowhere? It is like trying to see a single, faint thread in a tapestry when you are standing an inch away. Confirming the WIM existence and measuring its properties through the background is one of the most delicate tasks in modern cosmology. Success would not just solve a cosmic accounting error, It would complete our map of the ordinary matter in the universe, revealing the final, hidden architecture that connects all the brilliant structures we can see. That faint, all-sky glow is not just a record of violence. It is a potential map to the universe's hidden skeleton, a whisper of the warm filaments that tie the cosmos together. Even our own sun adds its voice to this cosmic chorus. Its outer atmosphere, a million-degree halo of plasma called the corona, constantly flickers with X-rays, flaring into intense bursts of high-energy light. Now magnify that single, familiar star by the hundreds of billions within a typical galaxy. Every one of those suns, especially the young, tempestuous ones and the fading remnants of dead stars, contributes its own faint X-ray whisper. From our distant perspective, the combined glow of all these stellar coronae blends into a soft, diffuse haze, a galactic foreground that lies superimposed across the deeper, extragalactic signal we are trying to measure. This creates a delicate puzzle of cosmic subtraction. To isolate the true background from the distant universe, astronomers must first create a perfect model of this closer stellar emission. They need to understand the X-ray personality of every type of star, from the raging tantrums of infant T-Tauri stars to the quiet, hot glow of white dwarf embers. Only by meticulously accounting for this galactic static can they hope to hear the faint, clear signal from beyond, a signal that holds the secrets of black holes and the missing matter of the cosmos. The challenge is immense, like trying to hear a single, distant conversation in a crowded, noisy room where every person is speaking at once. The faintest whispers in this cosmic static may be the oldest of all. We must push our search to the very edge of observable time, to an era before galaxies fully formed. A tantalizing possibility is that the most ancient component of the X-ray background comes from the universe's very first generation of black holes. These are the hypothetical population 3 black hole remnants. They would have been forged in the deaths of the first stars, colossal giants made only of hydrogen and helium, which lived fast, violent lives and collapsed directly into black holes. These primordial objects are the leading candidates for the seeds of all the supermassive black holes we see later in cosmic history. How does a black hole grow to weigh 1 billion times the mass of our sun? It must start from something, and these first black holes are that missing link. The mystery lies in the extreme challenge of finding them. Their individual X-ray signals would be incredibly faint, stretched and diluted by the expansion of the universe over billions of years, buried under the cacophony of all the younger, brighter sources. Disentangling this specific signal from the rest of the background noise is one of astronomy's ultimate goals. To detect it would be to uncover the fossil record of the cosmos's infancy, a direct glimpse into the chaotic nursery where the first monstrous gravity wells were born. This is not just about finding another class of object. It is about witnessing the very moment the universe planted the seeds for its future structure, a faint echo of creation itself, forever encoded in the X-ray fog that fills our sky. This faint, all-sky glow is not a uniform sheet of light. If you could examine it with perfect vision, you would see it is subtly mottled, textured with tiny variations in its intensity. These imperfections, known as anisotropies, are the next great clue. They are the fingerprints left on the cosmic background by the hidden sources themselves. The mystery lies in decoding these faint statistical whispers. What can the specific pattern of this clumpiness tell us about the objects we cannot see directly? Imagine you're standing outside a massive, darkened stadium. You cannot see the individual people inside, but you can hear the combined roar of the crowd. By carefully listening to the roar, you could learn a great deal. Is the sound a smooth, constant hum, or is it broken up by distinct cheers and chants from different sections? The size and loudness of those cheers would tell you if the crowd is made of many small groups scattered throughout the stands, or a few massive, densely packed blocks of people. This is precisely what astronomers do with the X-ray background. They study the statistical fluctuations, the tiny bumps and wiggles in the intensity of the glow. The size of these fluctuations on the sky is incredibly revealing. If the variations are very small and fine-grained, it suggests the background is dominated by an enormous number of relatively faint, closely packed sources. If the fluctuations are larger and coarser, it points to a population of brighter, more sparsely distributed objects. This analysis confirmed that the vast majority of the background comes from individual point sources like active galactic nuclei rather than a truly diffuse process. But it goes even deeper. By matching the observed fluctuation pattern to theoretical models, scientists can statistically probe the properties of the most distant and faintest sources, the ones that remain unresolved. It tells us about their typical luminosities and how they are clustered across the universe. This clustering is a direct echo of the underlying dark matter scaffolding, as galaxies and their black holes form preferentially in the densest knots of the cosmic web. So, by mapping the subtle texture of this X-ray fog, we are indirectly tracing the largest structures in existence, using the unresolved light of hidden black holes to illuminate the invisible architecture of the cosmos. The texture of the background is only one piece of the puzzle. Its color holds an even deeper secret. X-rays are not all the same. They come in a spectrum of energies, from lower energy soft X-rays to the piercing, high energy hard X-rays. When astronomers carefully dissected the color of this cosmic fog, they found something deeply puzzling. The background is harder than it should be. It is richer in those high energy, penetrating X-rays than any simple prediction could account for. If the glow were simply the combined light of all the active supermassive black holes we have already identified, its spectrum would be softer, gentler. The fact that it is not tells us we are missing an entire population of cosmic objects. Something out there is pumping out hard X-rays in vast quantities, and we have not properly found them all yet. This is the spectral hardness problem, and it forces a dramatic rethink of what is really contributing to the sky's permanent glow. There are two leading suspects for this spectral anomaly. The first is a hidden population of black holes that are even more heavily obscured than we previously thought. Picture a black hole buried under an incredibly thick cosmic blanket of gas and dust. The lower energy soft X-rays simply cannot fight their way through this shroud. They are absorbed, but the most energetic hard X-rays are like armor-piercing rounds. They have the power to punch through the obscuration and travel across the universe to our telescopes. So, what we would see is a sky that appears artificially hard because all the softer light from these objects has been filtered out on its way to us. The second possibility is even more exotic. What if there are entire classes of objects that are intrinsically hard? They might be black holes that operate in a different mode, perhaps with accretion disks that are inherently hotter or with particle jets that generate exceptionally high energy radiation. Or they could be something else entirely, like vast numbers of intermediate mass black holes, a missing link in black hole evolution that produces a distinct X-ray signature. Solving this spectral mystery is like being a detective at a crime scene where the light itself is the witness. By analyzing the precise energy of every X-ray photon in the background, astronomers are slowly building a case. They are working to determine if the culprit is a legion of deeply hidden monsters or a new type of cosmic engine altogether. The answer will rewrite our understanding of how black holes grow and how they have shaped the universe from the shadows. This cosmic glow is not a fixed photograph of the universe. It is more like a living, breathing entity, constantly flickering and shifting. The X-ray sky is a transient stage where sources flare into brilliance and then fade back into obscurity over days, weeks, or years. This variability is not a flaw in the data. It is a powerful tool. By monitoring how the light from these distant points changes, astronomers can classify them, almost like diagnosing a patient by their heartbeat. A slow, rhythmic variation might hint at the orbital dance of a binary star system, while a sudden, violent outburst could signal a star being torn apart by a black hole. Large-scale monitoring missions are essential for catching these cosmic performances, turning a single snapshot into a full-length movie of high-energy activity. This leads to a profound and unsettling question about the background itself. How much of this faint, persistent glow is not from steady sources at all, but from the accumulated afterglows of ancient, fleeting catastrophes? Picture a gamma-ray burst, the most powerful explosion since the Big Bang, or a tidal disruption event where a star is shredded by a supermassive black hole. These events blaze with incredible intensity for a short time, flooding space with X-rays before fading away. Their brief, brilliant lives are over, but their light continues to travel across the cosmos. The integrated glow from billions of these past explosions, each one a final, desperate signal, could be woven directly into the fabric of the X-ray background. The sky we see is therefore a palimpsest, a cumulative record written over by countless cosmic fires that have long since burned out. We are left to wonder if we are looking at a universe of stable, enduring powerhouses, or one filled with the silent, fading echoes of unimaginable violence. The faintest X-rays in this cosmic fog may be the oldest light of all, a direct whisper from the universe's first dawn. Billions of years ago, before galaxies as we know them existed, the cosmos was a dark, featureless sea of neutral hydrogen gas. Then something happened that changed everything. The first stars and black holes ignited, flooding the universe with its first intense radiation. This light began a monumental process called reionization, a cosmic dawn where these early objects burned away the primordial fog, transforming the neutral hydrogen into the transparent, ionized plasma that fills intergalactic space today. We know this event occurred, but its precise details remain one of the greatest mysteries in cosmology. What were the objects that provided the final, decisive flash? The most energetic radiation from these first sources would have been X-rays, produced by the earliest supermassive black holes or the violent deaths of the first stars. The tantalizing possibility is that the collective X-ray glow from this entire epoch of reionization is still traveling across the universe, subtly imprinted on the most distant, most ancient part of the cosmic X-ray background. Detecting this specific signal is like trying to isolate the very first spark from the glow of a city that was built over it. It is an incredibly faint whisper buried under the roar of all the younger, brighter sources that came after. But if we could find it, this would be more than just another data point. It would be a direct window into the universe's most important phase transition, the moment it was fundamentally transformed from a dark, simple void into a transparent, structured cosmos capable of hosting the galaxies we see today. This faint X-ray residue could tell us what truly ended the cosmic dark ages, revealing whether it was the gentle light of the first stars or the violent fury of the first black holes that ultimately cleared the fog and set the stage for everything that followed. Scattered throughout nearby galaxies are strange, brilliant beacons that defy simple classification. These are the ultraluminous X-ray sources, or ULCs. They shine with the power of millions of suns, yet they appear as mere points of light, far outshining any typical stellar black hole while falling short of the staggering output of a supermassive black hole. They are the cosmic middleweights, and their existence challenges our fundamental understanding of how black holes feed and grow. The central mystery is deceptively simple. What are they? One compelling idea is that we are finally seeing intermediate mass black holes in the wild. These would be the missing link between the stellar mass black holes, born from dying stars, and the supermassive giants that anchor galactic centers. An intermediate mass black hole could weigh anywhere from a few hundred to a few 100,000 solar masses, and its powerful gravity could readily explain the immense X-ray output of a ULEX. But there is another, equally fascinating possibility. What if they are just ordinary stellar mass black holes behaving in an extraordinary way? This would require them to break a fundamental rule known as the Eddington limit. Think of it as a cosmic speed limit for eating. As matter falls into a black hole, the intense radiation it produces pushes back, creating a balance that limits how fast the black hole can consume. To shine as brightly as a ULX, a stellar black hole would have to be consuming matter at a rate far beyond this theoretical limit. It would be gorging itself in a reckless, unsustainable feast. In this super Eddington mode, the accretion disk might puff up into a thick, dense funnel, or the system might somehow bypass the radiation pressure altogether, allowing for a brief, brilliant period of hypergrowth. The light from these objects would be uniquely intense, and if they were far more common in the chaotic, gas-rich early universe, their collective, integrated glow could have left a permanent mark on the cosmic X-ray background we observe today. So the question is not just what they are, but what they represent. RULX is the rare present-day examples of the long-sought intermediate black holes, the building blocks of galactic giants. Or are they showing us a temporary, violent phase in the life of a common star system, a demonstration of how even a small black hole can, under the right conditions, briefly impersonate a cosmic titan? The answer holds the key to a deeper truth about how black holes of all sizes have shaped the light of the cosmos since the very beginning. A star's final moments can be a spectacle of pure violence. Picture a sun, much like our own, on a routine orbit that takes it just a little too close to the supermassive black hole at the galactic center. The difference in gravity between the side of the star facing the black hole and the side facing away becomes so immense that the star is literally torn apart. It is stretched into a thin, superheated stream of gas, a process called spaghettification. As this stellar debris swirls into the black hole's accretion disk, it heats up to millions of degrees, unleashing a brilliant flare of X-rays that can outshine its entire host galaxy for months. This is a tidal disruption event, a fleeting but spectacular cosmic cataclysm. While each individual flare is temporary, they are happening all the time, scattered across the vastness of space and time. And this presents a fascinating possibility for the cosmic X-ray background. Could the accumulated light from all these stellar deaths, these ancient and distant flashes, be a permanent part of the faint glow we see today? The mystery lies in the numbers. How often do these events actually occur across the universe? If they are relatively rare, their contribution to the background would be negligible, a few scattered embers in a vast fog. But if they were far more common in the past, particularly in galaxies with denser stellar cores, then their combined time-averaged glow could be significant. It would be like the combined light from countless distant camera flashes, each one going off only once, but with so many of them that their brief illumination blends into a persistent, faint shimmer. Calculating this total contribution is a monumental statistical challenge. Astronomers must survey vast volumes of space to catch a few of these events in the act, then use those numbers to extrapolate a cosmic rate throughout history. They have to account for how the properties of galaxies and their central black holes have changed over billions of years, which would have directly influenced how many stars were devoured. The light from each event is not just a simple flash. Its specific X-ray signature, its brightness and duration, tells a story about the type of star destroyed and the mass of the black hole that did the destroying. This means the unresolved background could contain a fossil record of stellar demographics, a hidden ledger of how many stars of various sizes met their end in the crushing grip of gravity. So when we look at that smooth, all-sky glow, we might not only be seeing the steady light of hidden black holes, we could also be witnessing the final, fading echoes of countless stellar apocalypses, a permanent memorial to suns that were violently unmade. Before we can listen to the whispers from the edge of the cosmos, we must first quiet the noise from our own celestial backyard. Our Milky Way galaxy itself produces a faint, pervasive X-ray glow, a diffuse emission that acts like a shimmering veil draped across the entire sky. Peering through this veil to see the true cosmic background is one of the most delicate tasks in X-ray astronomy. This galactic foreground is not a single, simple light. It is a complex tapestry woven from three distinct threads. The first is the hot gas of the local bubble, a vast cavity in interstellar space that our solar system happens to be passing through. This bubble, likely carved out by ancient supernova explosions, is filled with a thin, million-degree plasma that softly glows in X-rays. The second thread comes from a more local and surprising process, a phenomenon called charge exchange. This occurs when ions from our own sun's solar wind, streaming outward into space, collide with and steal electrons from cold, neutral atoms drifting in the interstellar medium. This delicate theft produces a faint but measurable X-ray signature, a whisper of our own star's influence on its immediate surroundings. The third and most challenging component is the unresolved light from countless faint stellar sources within our galaxy. Millions of coronae from stars like our Sun, the hot remnants of dead stars, and distant binary systems all add their individual, tiny X-ray voices to a collective, diffuse hum. The great mystery is not that this glow exists, but how to create a perfect pixel-by-pixel model of it across the entire sky. Astronomers must become master sound engineers for the cosmos, tasked with building a filter that can remove this specific galactic static with absolute precision. Any error, any miscalculation in this model does not just add noise, it creates a phantom signal. A slight overestimation of the galactic foreground could make the extragalactic background appear artificially faint, causing us to miss a crucial component. Conversely, underestimating it could invent a false signal, making us believe we are seeing a new cosmological phenomenon when we are really just seeing the unresolved glow of our own galaxy's stellar inhabitants. The quest to isolate the true cosmic background is therefore a profound exercise in self-knowledge. To understand the universe beyond, we must first understand the intricate, glowing shell of our own galactic home with absolute clarity. Two great glows illuminate our universe, but they tell two entirely different stories. You are likely familiar with the cosmic microwave background, that famous afterglow of the Big Bang that paints the sky in the faint warmth of microwaves. It is the oldest light we can see, a baby picture of the cosmos when it was a mere 380,000 years old, a hot, dense, and incredibly smooth soup of particles and energy. The cosmic X-ray background is its polar opposite. This is not a relic of a hot, dense beginning. It is the cumulative record of everything that came after. It is the story of a universe growing up, becoming lumpy and structured and violent, where the microwave background shows us a cosmos of stunning uniformity. The X-ray background reveals the magnificent clumps and scars of its evolution. One is the portrait of a calm, featureless infant. The other is the boisterous autobiography of its turbulent adolescence and adulthood. The mystery lies in reading these two texts together. The CMB provides the pristine starting conditions, the blank canvas upon which gravity could begin its work. Tiny fluctuations in that ancient heat map are the seeds, the blueprints for all the structure we see today. The cosmic X-ray background then shows us the final, fiery outcome. It is the light emitted as those seeds grew into the grand cosmic architecture of clusters, filaments, and the supermassive black holes that power active galactic nuclei. The CMB tells us how the universe began its journey. The CXB chronicles the dramatic and often violent events that shaped it along the way. This is a profound duality. One background is passive, a fossilized echo from a single primordial moment. The other is active, a living chronicle being written even now by the most powerful engines in existence. So the next time you see an image of the cosmic microwave background, remember that its serene, mottled surface is only the prologue. The rest of the story, a saga of chaos and creation, is written in the high-energy X-ray glow that permanently bathes the cosmos. These cosmic monsters may be the great regulators of the universe. The violent energy pouring from an active supermassive black hole does not just vanish into the void. It slams back into its own galactic environment with the force of a perpetual storm, a process known as feedback. Imagine a vast cloud of cold gas, the raw material for building new stars. Now picture a hurricane force wind generated by the black hole's own radiation blasting through that stellar nursery. This wind heats the gas, pushing it away or even driving it entirely out of the galaxy. This is the missing feedback cycle, a self-regulating mechanism that could explain one of the great cosmic puzzles. Why did the era of rapid star formation in the universe eventually come to an end? The cosmic X-ray background holds the key to tracing this process on a grand scale. The hot gas that is heated and stirred by these black hole winds glows brightly in X-rays. If this feedback is as powerful and widespread as theories suggest, then the combined emission from all that agitated gas across all of cosmic history should be subtly woven into the very fabric of the background glow we observe. The central mystery is one of efficiency. How much gas is truly being heated or expelled? Is this process the primary reason why giant elliptical galaxies are often described as red and dead, cosmic retirement homes filled with aging stars and devoid of the fresh gas needed to birth new ones? The data from the background offers a unique statistical way to answer this. By carefully analyzing the properties of the unresolved X-ray light, astronomers can estimate the total amount of hot gas that has been processed by these winds over billions of years. This is not about studying one galaxy at a time, but about reading the summed result of countless galactic battles between creation and destruction. The lingering question is whether black hole feedback is a precise thermostat, gently turning down star formation, or a brutal hammer that shuts it off completely. The faint X-ray fog that fills our sky is the cumulative echo of that epic struggle, a permanent record of how the universe's most destructive forces may have also been the architects of its current quiet state. This faint X-ray fog might originate from the very fabric of the cosmos itself. Some of the most profound theories in physics propose that dark matter, the universe's invisible scaffolding, is not entirely stable. What if these mysterious particles could slowly decay or annihilate each other, transforming their mass into pure energy? This process would inevitably produce radiation, including X-rays, as a final, ghostly byproduct. In this extraordinary scenario, a specific portion of that smooth, unresolved glow we see across the sky would not be from black holes or hot gas at all. It would be the collective funeral pyre of dark matter, a universe-wide signal of its slow transformation playing out in every cubic light-year of space. The search for this signal is a meticulous forensic exercise. Astronomers are not looking for a broad, fuzzy hum of energy. They are hunting for something far more precise, a single, sharp spike at a very specific energy level in the X-ray spectrum. This would be a spectral line, an unmistakable fingerprint left by a particular type of particle as it vanishes from existence. The mystery is that we do not know exactly what energy that line should be at. It depends entirely on the unknown mass of the dark matter particle itself. So scientists must scan the cosmic X-ray background, line by line, energy by energy, searching for a single, anomalous spike that has no business being there. They must prove that this signal could not possibly come from any known astrophysical object, no matter how obscure or distant. It cannot be explained by the combined light of active galaxies, the heat of galaxy clusters, or the faint glow of stellar coronae. If such a line were found, it would be one of the greatest discoveries in the history of science. It would finally rip away the veil on dark matter, revealing not just its presence through gravity, but its fundamental identity. We would know what it is made of, and we would have witnessed its secret life playing out across the entire cosmos. That faint, all-sky glow we have been deciphering would then be more than a record of cosmic violence. It would be a direct message from the invisible majority of the universe, a permanent whisper of the dark side decaying into light. Every mystery we have explored is filtered through a technological lens. Our view of the cosmic X-ray background is not a perfect window, but a picture painstakingly assembled by machines of incredible yet finite capability. The fundamental challenge begins with the light itself. X-rays are so immensely energetic that they do not behave like ordinary light. If you try to focus them with a standard glass lens, they would simply pass straight through or be absorbed. To bend these stubborn photons, engineers had to devise a completely different solution, a technique known as grazing incidence. Imagine skipping a stone across the surface of a pond. The stone does not plunge in immediately, it glances off the surface at a shallow angle. X-ray telescopes work on a similar principle. They use nested, cylindrical mirrors, polished to an atomic smoothness, that are positioned almost parallel to the incoming X-rays. The photons just graze the surface, redirecting them ever so slightly toward a focal point. It is an elegant, complex workaround, but it comes with inherent limitations. These grazing mirrors collect only a tiny fraction of the available light, like trying to catch rain with a sheet of paper held almost flat. This constraint dictates the size, cost, and ultimate sensitivity of every X-ray observatory we build. Missions like Chandra, XMM Newton, and more recently eROSITA are triumphs of this technology. Chandra provides exquisitely sharp vision, allowing us to resolve millions of point sources. XMM Newton acts as a light bucket, gathering vast numbers of photons for detailed spectral analysis. eROSITA is performing an all-sky survey of unprecedented depth. Yet for all their power, they are like listening to a symphony with earplugs. Their sensitivity has a hard flaw. They can only detect sources above a certain brightness, leaving the faintest whispers buried in the noise. Their energy resolution, the ability to distinguish between X-rays of subtly different energies, is limited. This means the precise spectral fingerprints of distant gas or decaying dark matter are blurred, their secrets remaining just out of reach. The unresolved portion of the background is therefore a dual mystery. It is a question of astrophysics, of what is actually out there, but it is equally a question of pure engineering. What are we simply not yet capable of seeing? The next generation of telescopes, like the proposed Athena and Lynx missions, are designed to shatter these barriers. Athena will have a collecting area more than 100 times larger than current observatories, allowing it to gather X-rays with stunning efficiency and measure their energies with a precision we can only dream of today. Lynx aims for vision even sharper than Chandra's, capable of seeing the faintest, most distant objects as clear points of light. With these tools, the fog will not just be resolved, it will be dissected. We will see the individual stellar corpses in distant galaxies, map the warm, hot intergalactic medium directly, and scan for the specific, sharp spectral line of dark matter decay with crystal clarity. The greatest discoveries in X-ray astronomy may not be what we have already found, but what our current instruments are physically incapable of showing us, a hidden universe waiting for the right eyes to see it. These dark spots in our cosmic map are the cross-match conundrum. To truly understand what an X-ray source is, you cannot look at it in isolation. Astronomers perform a kind of cosmic triangulation, taking the precise coordinates of an X-ray flash and searching for its counterpart in other kinds of light. They look for the same point in the sky in optical surveys from telescopes like Hubble, in the infrared eyes of Spitzer, and in the radio whispers picked up by vast antenna arrays. Most of the time, this works beautifully. An X-ray source aligns with the brilliant core of a distant galaxy in an optical image, confirming it as an active supermassive black hole. But a stubborn fraction of these X-ray sources are complete orphans. They blaze in the high-energy sky, and yet when you look at that exact same spot with every other type of telescope we have, there is nothing there at all. Just an empty patch of darkness. So what are these ghosts? One compelling possibility is that they are active galactic nuclei from the very edge of the observable universe. Their visible and infrared light has been stretched so far by the expansion of the cosmos that it has been redshifted into a part of the spectrum our current telescopes cannot detect. We see only their penetrating X-rays, which are less affected by this cosmic stretch, a final beacon from an impossibly distant dawn. Another idea is that these are the most heavily obscured black holes of all, buried under such impenetrable, thick cocoons of dust that not even infrared radiation, which can usually peer through haze, can escape. Only the most powerful X-rays make it out, like a single, desperate signal from a prison of gas and dust. The most exciting possibility, however, is that these orphans represent something entirely new. They could be a class of object we have not yet predicted, cosmic engines that operate in a way we do not yet understand, shining brightly in X-rays but remaining dark across the rest of the electromagnetic spectrum. This conundrum is a humbling reminder that our view of the cosmos is fragmented, built from the narrow windows of light we have learned to open. Each orphan source is an unanswered question, a quiet promise that the universe still holds engines of creation and destruction we have not yet dreamed of. Our own galactic neighborhood teams with violent partnerships, often hidden in plain sight. These are X-ray binary systems, celestial dances of theft and fury. Picture a binary pair, two stars locked in a gravitational embrace. One star evolves, dies, and collapses into an ultra-dense remnant, a neutron star or a stellar mass black hole. If the two objects are close enough, the intense gravity of this compact corpse begins to steal gas directly from the outer layers of its living companion. This stolen matter does not fall in quietly. It spirals inward, forming a searingly hot accretion disk that glows with tremendous intensity, pouring out X-rays. A single one of these systems can outshine our sun by a factor of 1,000,000 in this high-energy light. Now multiply that by the hundreds of billions of stars in a single galaxy like our own. Then multiply that by the hundreds of billions of galaxies scattered across the cosmos. The combined light from all these faint, distant stellar dramas adds its own persistent whisper to the cosmic X-ray background. The central challenge is a monumental census. How do we accurately count something we cannot see directly? We must rely on population statistics, building a cosmic model from the relatively few binary systems we can study up close in our own galaxy. We have to understand their life cycles, how often they form, how long they shine, and how their X-ray output changes over time. But this is where the mystery deepens. The population of these binaries is not the same in every galaxy. A young, spiral galaxy rich in gas and massive stars will have a very different cast of characters than an old, elliptical galaxy filled with ancient, lower-mass stars. The types of binaries that form and their X-ray brightness depend entirely on the stellar environment. So, to estimate their total contribution to the background, we need to know not just how many binaries exist, but what kinds of galaxies they lived in throughout cosmic history. Were they more common in the gas-rich galaxies of the early universe? Did they shine brighter or longer? If we overestimate their collective glow, we might mistakenly attribute that portion of the background to more exotic sources, like hidden supermassive black holes. But if we underestimate it, we could be inventing a mystery where none exists, searching for new physics in a signal that is just the accumulated flicker of countless stellar thieves. This is the delicate work of cosmic accounting, a reminder that the grandest background glow is built in part from the intimate chaos of stellar pairs. This cosmic web is not just a map of the galaxies we can see. Its invisible architecture is subtly stamped upon the X-ray background itself. Think of the millions of active black holes that create this glow. They are not scattered randomly through the void. Just like visible galaxies, they trace out the dense knots and filaments of the dark matter web, congregating in the universe's most crowded neighborhoods. This means the faint X-ray fog should not be perfectly smooth. It should carry the faintest imprint of the cosmic web's grand design, a textured pattern of its own. Astronomers hunt for this pattern using a powerful statistical tool called the correlation function. It is a way to measure the hidden clumpiness in the background's glow. They ask a simple but profound question. If you pick a random bright speck in this X-ray fog, how much more likely are you to find another bright speck a certain distance away compared to a completely random distribution? This tendency for sources to cluster, to have cosmic neighbors, reveals everything. The specific scale of this clustering is a direct echo of the underlying dark matter scaffolding. It tells us about the gravitational wells where galaxies and their central black holes were born and grew. By measuring this imprint across different depths, scientists can essentially make a movie of cosmic structure formation. They can see how the clustering of X-ray sources changes over billions of years, testing our most fundamental models of how gravity sculpts the universe. Does the growth of these structures match the predictions of Einstein's general relativity, or does the subtle pattern in the X-ray background hint at something else? A need to revise our understanding of gravity itself on the largest scales. Extracting this signal is like trying to hear a single, consistent rhythm within the roar of a massive crowd. It requires exquisitely sensitive maps and a deep understanding of every other possible source of clutter. But if we can read this imprint, the X-ray background transforms from a simple record of individual sources into a dynamic chart of the cosmos's evolving skeleton, a hidden map written in the light of a billion black holes. Even the deepest field image is just a tiny window into an immense cosmos. When astronomers point a telescope like Chandra at a single, dark patch of sky for weeks, they are not surveying the entire universe. They are peering through a keyhole. The millions of sources they find in that one narrow field of view create a specific, local measurement of the X-ray background's makeup. But what if that particular keyhole just happens to be aimed at an unusually crowded or an unusually empty part of space? This is the cosmic variance problem, a fundamental uncertainty that arises from our own limited perspective. The structures of the universe, the clusters and the vast voids, are not distributed with perfect uniformity. One tiny patch might contain a rich supercluster, artificially inflating the number of sources we see. Another might be centered on a cosmic void, making the universe appear quieter and more empty than it truly is. So the great mystery becomes one of statistics. How can we be sure that the conclusions we draw from these precious deep fields are truly universal, and not just a description of one random, unrepresentative neighborhood? This uncertainty is not a simple error bar that can be easily reduced. It is a fundamental limit imposed by the fact that we have only one universe to observe, and we are stuck in a single location within it. We cannot step outside and take an average of 1 million different cosmic deep fields to find the true mean. We have to work with the handful of keyholes we have. Astronomers combat this by taking multiple deep fields in widely separated directions across the sky, hoping to sample different large-scale environments. They then use sophisticated models of the cosmic web to estimate just how much the counts of galaxies and black holes are expected to fluctuate from one patch to another. But the variance itself is a source of information. The amount of fluctuation from field to field tells us something about the size and scale of the underlying structures. If the source counts very wildly, it suggests the universe is very clumpy on large scales. If they are more consistent, it implies a smoother distribution of matter. So the cosmic variance is both a problem to be solved and a signal to be measured. It forces a profound humility, reminding us that every map we make of the cosmos is not just a picture of what is out there, but also a reflection of our own singular and limited point of view. At the extreme end of the energy spectrum, the cosmic X-ray background takes on a sharper, more penetrating character. This is the high-energy tail, a domain of the most powerful and elusive X-ray photons. While the overall fog has been largely resolved into points of light, this particular band remains stubbornly enigmatic. Its sources are not just faint, they are fundamentally different, emitting a kind of radiation that is incredibly difficult to produce and even harder to trace. The hunt for the origin of these hard X-rays is like searching for a specific type of ghost, one that leaves only the most fleeting and energetic footprints. What cosmic engines are capable of generating such piercing light? One strong candidate brings us back to the most heavily shrouded active galactic nuclei. Imagine a black hole buried under a mountain of gas and dust so immense that it acts like a cosmic filter. The lower energy, softer X-rays are completely blocked, absorbed by this thick shroud. But the highest energy photons are like bullets. They possess enough raw power to punch straight through the obscuration and travel across the universe to our detectors. What we see, then, is an artificially hardened signal. The background appears rich in these high-energy X-rays because all the softer light from these hidden monsters has been stripped away on its journey to us. This creates a profound observational bias, suggesting a vast, unseen population of black holes in their most heavily veiled state. Yet there is another, even more dramatic possibility. Perhaps these hard X-rays are not from thermal processes, like the simple heat of a hot gas, but from non-thermal events. Think of the difference between the steady warmth of a stove burner and the brilliant, instantaneous spark of a static shock. In the vast spaces within galaxy clusters, particles can be accelerated to nearly the speed of light by shock waves or turbulent magnetic fields. When these relativistic particles collide or spiral in magnetic fields, they emit a distinct, hard form of radiation through a process called synchrotron emission or inverse Compton scattering. The collective crackle of these particle accelerators, scattered throughout the cosmic web, could be imprinting its signature onto the high-energy tail of the background. And then, of course, there is the most exotic prospect of all. Could this signal be the final, faint whisper of dark matter itself? Certain theoretical particles, like sterile neutrinos or WIMP, are predicted to decay or annihilate each other, producing X-rays at very specific high energies. A smooth, unresolved component in this hardest part of the spectrum would be a prime candidate for such a signal, a universal glow from the slow transformation of the invisible universe into pure light. Pinpointing the true origin of this high-energy tail is one of the final frontiers in X-ray astronomy. It requires telescopes with unprecedented sensitivity at these punishing energies, instruments that can distinguish between the filtered scream of a hidden black hole, the faint crackle of a cosmic particle accelerator, and the ghostly line from a decaying dark matter particle. The answer will not only tell us what we are seeing, but will ultimately reveal which of the universe's most violent or most secretive processes holds the final key to this enduring cosmic mystery. The ultimate challenge is not finding more pieces but fitting them all together. After decades of discovery, from hidden black holes to the cosmic web's hot gas, we face a final, grand synthesis. Can we build a single, unified model that perfectly explains every photon in the cosmic X-ray background? This is the meta-mystery, a puzzle that encompasses all the others. The goal is a cosmic ledger of breathtaking precision, one that accounts for the roar of unobscured active galaxies and the filtered scream of their deeply buried cousins. It must include the diffuse heat from galaxy clusters and the whisper-thin glow of the warm-hot intergalactic medium. It needs to budget for the combined flicker of countless stellar binaries in distant galaxies and leave room for any exotic contributors, from the remnants of the first stars to the possible decay of dark matter. This model must hold true across the entire spectrum of X-ray energies, from the softest glow to the most penetrating hard rays, and it must remain accurate across all of cosmic time, from the recent universe back to the deepest redshifts of the cosmic dawn. Current models are remarkably good, a testament to our growing understanding, but they are not perfect. Tiny discrepancies remain, small mismatches between the predicted and the observed glow. These are the ghosts in the machine, the missing or mischaracterized components that prevent a complete accounting. Perhaps we have underestimated the number of the most heavily obscured black holes, or overestimated the collective output of stellar systems in the early universe. Maybe the warm-hot intergalactic medium contributes more or less than we currently calculate. Or perhaps there is a faint, pervasive signal from a process we have not yet even considered, woven throughout the background's fabric. This final puzzle represents the ultimate goal, the culmination of the entire scientific journey that began with that accidental discovery in 1962. It is the quest to write the definitive biography of the high-energy universe, to close the ledger and declare that we finally understand the precise, combined echo of all the violence, heat, and hidden structure that has ever illuminated the cosmos. So there you have it, 25 mind-bending mysteries all woven into the faint, high-energy fog that permanently bathes our cosmos. From the hidden feeding frenzies of supermassive black holes to the possible, ghostly decay of dark matter itself, the cosmic X-ray background is so much more than a simple glow. It is a history book, a physics laboratory, and a treasure map all rolled into one. This pervasive light reminds us that our seemingly quiet universe is a stage for constant, invisible violence and transformation. It whispers that for every question we answer, a dozen more are waiting in the shadows. Now we want to hear from you. Which of these cosmic riddles captures your imagination the most? Is it the deeply shrouded black holes, the search for the universe's missing matter, or the haunting possibility that we are seeing dark matter itself fade into light? Let us know your thoughts in the comments below. If you enjoyed this journey to the edge of our understanding, please show your support by liking this video, subscribing to the channel, and hitting the bell icon so you never miss our next adventure into the cosmos. Thank you for watching.